This is going to be review video number 12, how to draw Lewis structures. So starting out, what is a Lewis structure? It's a flat drawing, and it's going to show two things, most predominantly. One, it's going to show you the valence electrons, or the outermost electrons of any atom in a compound, and it's going to show the relative position of all the atoms within that compound. The reason that we draw them is because we can use Lewis structures to predict the shape of molecules, which is called VSEPR, which I'll go over in a different video. And it allows us to predict not only the shape of an overall molecule, but the shape of different groups of atoms if that molecule happens to be large. Shape names that you may have heard of before: linear, bent, tetrahedral, trigonal, planar, all of those fun stuff. And the reason that the shape in and of itself is important is because it allows us to predict bonding patterns and how certain molecules will interact with other molecules. And you'll get the opportunity to predict some of those things going forward. The first thing I want you to be able to do, though, is draw Lewis structures. It's going to be super important for this class. It's going to be super important for the AP test, so you absolutely do have to know how to draw Lewis structures. We're going to look at these different steps through the lens of this molecule CF4. So the first rule for drawing a Lewis structures is we have to decide which atom in the molecule is going to go in the middle of our structure and which ones are going to be distributed around it. So there's a couple of things to pay attention to there. The atom that can bond the most amount of times is going to be the one that goes in the middle. Usually, that is going to be the atom that you have the least amount of. Which, if we're looking at CH4 up here, that's going to be carbon, right? We have the least amount of carbons. There's only one of them, whereas we have 4 fluorines. So it makes more sense for carbon to go in the middle. Not only that, but carbon is just special because it can bond a lot of times, so usually carbon is going to be your middle guy. If there's a ton of carbons in a molecule, you would make a chain. You would just put a bunch of carbons next to one another and then move on. So let's do that real quick. We have our carbon in the middle, and we're going to put our fluorines, all 4 of them, equally around that carbon. That's step 1. Done. All right. Step 2 says to draw the electron dot diagrams around each atom. Remember, when you're drawing an electron dot, you only start pairing up the electrons after 4. So you can see down here that carbon has 4 valence electrons, and so all of those would remain unpaired. But nitrogen has 5. So when you draw that out, you're going to do 1, 2, 3, 4, and then pair up the 5th one. And if you're wondering where I got this information, how I know that carbon and nitrogen have 4 and 5 valence electrons respectively, it has to do with their group on the periodic table. Carbon's in group 14, so it has 4. Nitrogen's in group 15, so it has 5. All right? So let's go back up here and let's draw our electron dots for every single atom. We know carbon has 4 because it's in group 14, so I'm just going to draw those 4 dots. Fluorine is in group 17, so it's going to have 7 valence electrons. And remember, we only start pairing them up after 4. So we draw 1, 2, 3, 4, 5, 6, and 7. You'll notice that I put the unpaired one in the middle, which is important because I'm going to need to draw lines after I finish my electron dot structures. So just make sure that you are keeping track of where your unpaired electrons are located. All right, so I'm just going to draw my others around the rest of my fluorines. All right, that's done. 3. Our next rule is to connect unpaired electrons on adjacent atoms to form bond lines. So unpaired electrons can form bonds. Paired electrons tend not to. There are absolutely exceptions to that. We will learn how to split pairs and violate octet rules in class. But for just simple Lewis structures, if you can avoid splitting a pair, avoid it. right? So this is a pair on this nitrogen here, and so it's not going to bond with anything. However, we see that there's an unpaired electron on nitrogen and an unpaired electron on this hydrogen, so we can draw a line between them, and we call that a bond line because those two electrons are going to be shared between the nitrogen and the hydrogen here. All right, so let's go up here and let's draw our appropriate bond lines. I'm going to draw one here, here, oops, that looks kind of messy, here, and here. All right, cool, that's done. Rule 4 says clean up your structure. It has to be pretty. You cannot have really gross looking messy structures. I will mark you wrong for that. The AP test will mark you wrong for that. It has to be pretty. So a couple of things that you want to make sure you clean up. We can't have any weird curvy bond lines. So these couple blue lines that are curving around, no, absolutely not. Also, you got to get rid of any dots on the end of your bond lines. So a lot of people, especially in regular chem, because we teach them how to do this the same way, they'll leave these dots on the end of their bond lines. And while I don't personally have a problem with it, AP test people might. It depends on your grader. So I need you to clean up your structure. And by that, I mean getting rid of those little dots on the end of your line. So your structure should be clean, it should be nice, it should be pretty, just like this one over here. So let's take a quick look at our structure up top and see how we have to clean it up. The only thing that's wrong with this that I'm seeing is I'm seeing those little dots on the end of the bond line. So I'm just going to redraw it real quick. I just have those clean lines coming off of carbon. And for each of my fluorines, the only dots I'm going to redraw are the non-bonding pairs. So that would be these three on every single one of them. All right, so this is our clean, pretty structure at the end. I'm just going to go through a couple of examples with you just so that you know what's going on with some atypical Lewis structures that aren't super simple like CF4 was. In this first example up here, we have HCN, or hydrogen cyanide. In this one, there's not a clear atom that goes in the middle on first glance. We have one hydrogen, one carbon, and one nitrogen. But remember, carbon is usually your middle guy. So I'm just going to put carbon in the middle, and I'm going to put nitrogen and hydrogen on either side because we are going to evenly distribute the other two. Step 2 is draw your electron dots. So many people try to start drawing lines and then they do it wrong because they don't know how many lines need to be drawn. So don't do that. Just draw your dots first. I know it involves erasing later, but you're going to do it correctly, which is helpful. Hydrogen has one valence electron because it's in group 1. Carbon is going to have 4 because it's in group 14. And nitrogen is going to have 5 because it's in group 15. Next, we start drawing bond lines. I'm going to draw the obvious one between hydrogen and carbon, and then we got to look at what's left over. We know these guys are going to bond, but what I'm noticing is that I have 2 unpaired electrons on both carbon and nitrogen, and if that happens, they end up scooting to the center and forming bonds, right? So we're going to draw a bond here, and we're going to draw a bond there, right? The problem with this is that that structure is not very pretty. So we got to clean it up. We're going to have H, C, and then all of those lines need to be super pretty in the middle. And then that lone pair is still on nitrogen. So this would be your final structure for HCN. All right. This last one, C2H4O, is just a bigger molecule. And so when you're looking at a bigger molecule, it can be a little bit challenging to figure out where to start. But again, deciding where to put your middle atoms is super important. So I see that there are 2 carbons. So I'm going to put them next to one another. I also see that I have an oxygen. Oxygen can be a middle atom, but it can be a side atom. And so I'm just going to go ahead and put it on the end here. And we're going to distribute our hydrogens in just a second. So I'm just going to hold off on my hydrogens real quick. I'm going to draw my electron dots for all 3 atoms that I have, and we're going to see where hydrogens might fit. I know that each carbon has 4, and then oxygen is in group 16, so it's going to have 6. All right, so now I have 4 hydrogens that I need to distribute, right? I know, because this is all one molecule, that there's probably going to be at least a bond between all of those, right? Now, what I have is I have open slots for other things, right? I have 1, 2, 3, 4, 5, 6 spaces that I could theoretically put a hydrogen, but I only have 4 hydrogens to distribute. And when you see something like that, it means there's probably either going to be a double bond somewhere or a triple bond somewhere, depending on what you have. All right? So what I'm going to do is I'm going to double bond carbon and oxygen, because why not? Let's just do that real quick and see what happens. I'm going to put a weird, gross, curvy looking bond there, but it does tell me that I've used up those unpaired electrons. Now, what I have is 1, 2, 3, 4 areas where I can put a hydrogen, and I have 4 hydrogens, which is really nice. So I'm just going to put them where they go. And I can go ahead and draw those bond lines. Last step is to clean up my structure, right? So I'm going to redraw it without the gross curvy lines, without any of the dots, and it's going to look a lot prettier. So we have that structure, and it looks really pretty and really nice. One thing that I do want to point out, though, is that there is another option for this particular molecule, which is why it's the example that I'm using. Some molecules have more than one option for structures, and that becomes important in organic chem, because different molecules that have the same formula but different structures can react differently, and so on and so forth. For right now, you just need to know that different options exist. So what I'm going to do real quick is I'm going to go back and I'm going to erase some of these lines and the hydrogens, and we're going to look at the other option that was available to us. All right, so instead of choosing to double bond this oxygen to the carbon, I could have instead chosen to double bond these 2 carbons over on this side, right? So I could have chosen this option instead. And if I do that, that means that the placement of my hydrogens is going to change a little bit. So I would have put a hydrogen over here. I would have put one here. And I would have put one here. Whoops. Here and here. Right? And that still uses up all of the open unpaired electrons, and it's still a valid structure. It's just organized a little bit differently. So let's clean that one up and look at what it looks like. All right, so we're comparing this one now with this one. Both of these structures, perfectly valid. Both of those structures exist. And so in a testing environment, no matter which one you chose, that's fine. Unless there's language in a question that tells you that the oxygen has to be double bonded or the carbons have to be double bonded or something like that, either one of these would be fine. And so however you choose to interpret your structures is okay. If you have any problems trying to figure out how to